So we have introduced the concept of directional derivative. For function f defined near a and L is a direction, the directional derivative at a in the direction L is the phi prime 0, which is the limit f a plus tl minus f a to t. Here phi is the function minus epsilon. Phi t is f a plus tl. Okay, this is the directional derivative. It is the generalization of the partial derivative we introduced previously. So, and we also denote the directional derivative by dl f a. Okay, a much simpler notation. So, when a function has directional derivative along a given direction at a given point, this is a basic problem, and it turns out that if the function is differentiable at the point, then the result will be very good. Okay, this is our theorem. If f is differentiable at a, then for any direction L, the directional derivative of f at a in the direction L equals the gradient of f at a and the L inner product. Okay, note that the differentiability of f at a implies that for every I, the partial derivative difa exists. So because all the difa exist, therefore the gradient exists. Okay, because the gradient is a vector whose components are the partial derivative of f at a. Now the proof of this theorem is also very simple. Simple. Okay, proof. Because f is differentiable at a, as h goes to 0, our f a plus h minus f a will be the gradient of f at a, taking inner product with h and the norm higher order small than the norm of h. Now we let in this equality we let h to be tl. L is the given direction in the theorem. Okay, then as t goes to 0, h goes to 0. Obviously, L is a given vector unchanged. When t goes to 0, the norm of h is the absolute value of t multiplied the norm of L. Of course, this goes to 0. Therefore, the above equality becomes the left hand side is fa plus tl minus fa, and we divide by t, which is the right hand side. The right hand side, the gradient term will copy here, and the h is tl, but we have divided by t, so this is l. Okay, here the t is we take h equal to TL, and then divided by t on both sides of the previous equality, divided by t here. So the h here is TL, but the t is divided, therefore we only have L here. Then plus the norm of h is the absolute value of t. So this is t divided by t. Okay. Now we let t goes to 0. And the left hand side is the directional derivative at the point A by definition. If the limit of the right hand side exists, then the limit of the left hand side exists, and is the directional derivative. So the limit of the right hand side exists. Okay, so the limit of the right hand side is exactly the gradient of FAA and the inner product of the gradient and the L. So this proves the theorem. Okay, so the proof is very easy, but the conclusion is very important. This equality tells us some very useful information. Okay. So by this theorem, we can say that the direction of the gradient, or the gradient is the direction in which f increase the fastest. The most fastest. Okay, this means along all unit vector L, unit vector, the norm is 1. The directional derivative attains when L change. This is a function of L. You take A is fixed. You take different direction L, you get different directional derivative. So the directional derivative depends on L. Therefore, it's a function of L. So this function attains its maximum. The maximum is exactly the gradient, the norm of the gradient, at the direction which is the direction of the gradient. But because we restrict ourselves to the unit vector, so you need to normalize it to get a unit vector. Why this is true? Because if the norm of L is 1, then the directional derivative by the previous theorem is the gradient and the L. Now by Cauchy-Schwarz inequality, this will not greater than the norm of the gradient multiplied the norm of L. But L is a unit vector, so this is the norm of the gradient. When this is equality hold, equality if and only if L and the gradient has the same direction. That is, L is the L0, the normalized gradient. Okay, so this is the meaning of the gradient. The gradient. Now we can also state some interesting properties of the directional derivative. So we state the proposition here. If f is differentiable at A, then moreover K and L are two directions. C is a real number. What can we say? Then the gradient, the directional, K and L are two directions or two vectors. Their sum here is a new direction obtained from K and L by addition. Okay, so the directional derivative of f at A along this new direction is the sum of the directional derivative along these two directions. Okay, and also a scalar multiplication to L obtain a new direction CL. So along this new direction, the directional derivative is the multiplication of C and the original directional derivative. Okay, the proof of this proposition is quite easy. Using, for example, you can apply the gradient equality, and employ the basic property of scalar product or inner product. So I will not prove this proposition here because it is straightforward from the on the red equality on the left upper corner of this page. Okay.